Okay, so we're just taking our exponential ideas that we did from last time and applying them to these two problems right here. For the first one, suppose 30 flower beetles. What are flower beetles? Beetles that are made of flour. Maybe they eat flour. Maybe they hang out around flour. Or maybe they look like flour. I don't know. Does it matter what they are? No, it doesn't matter at all. Solve the math problem. Don't worry about what the flower beetle looks like. Maybe it's actually a dung beetle. It's just white. It's an albino dung beetle. How about that? They're left undisturbed in a warehouse bin. Why would you bother them? They're in the flour. You just want them there, right? Eat as much flour as you can, you beetles. The beetle population doubles each week. Of course it does. They have all the flour they want in this warehouse, and you're not bothering them. So the population doubles each week. The function, and look, they give you the function right here. 30 times 2 to the x power gives the population after x weeks. How many beetles will there be after 56 days? What are we going to do? Plug in what? Plug in 56? Yeah, notice it says x is in weeks, x weeks. And then they try to pull a fast one on you and say 56 days. Well, that's a problem because we don't have weeks, we have days. So how many days are there in 56 weeks? I'm sorry, how many weeks are there in 56 days? 8? How do you know? Because there's 6 days in a week? There's 7 days in a week. So if there's 7 days in a week, then how many weeks does it take to get to 56 days? Probably got to do 56 divided by 7, right? What is that? 8? 8 weeks. I make no sense? Yeah, I don't even know what I'm talking about. I'm just making stuff up as we go. Okay, so now I know how many weeks we're talking about here. I'm going to leave those beetles alone in my warehouse with all of my flour for 8 weeks. It's like a game I'm playing. I'm going to go see how much beetles I have. And then probably be sad. Could be. Could be the going rate for flower beetles is like the price of gold at this point. $1,700 an ounce. I do like beetles. Anyway, we want to find out how many beetles we're going to find when we go into that warehouse. So what do? Now we plug it in. And notice they gave me function notation right there. And I'm plugging in 8 for x, which means I'm going to write f of 8. That's just like a name. Doesn't mean I do anything with it. I'm just writing f of 8. And then I find my answer. And then I write 30 times 2, what? To the 8th power. And then I'm probably going to plug that all into my calculator. Because I have no idea what 2 to the 8th power is, even though I could figure it out by hand. What is it? 7,680 what? Beetles. Is that a lot of beetles? That's a lot of beetles. Some of them may have died after 8 weeks, but they're probably pretty happy. Yeah. So that's the answer, 7,680 beetles. By the way, just as an aside, how many beetles did I start with? How do you know it's 30? Because it says 30. Well, where did that 30 show up in my equation? Right there. How come that is a 30? If I start with 30, how many weeks have gone by? None. 0, right? 0 weeks. So if I plug in 0 right here, I'd have 2 to the 0, which is what? 1. And then I'd have 30 times 1, which is 30. So when 0 weeks has gone by, I have 30 flower beetles. Exactly what they told me that I had. So it makes sense that this number right here is the starting amount, however many you had. So if I told you that actually we started with 105 flower beetles, how would my equation right here change? Exactly. It would be 105 times 2 to the x power. Now it also says we're doubling each week. What number means doubling? Times 2. And do you see a times 2 somewhere in this problem? Yep, sitting right there. What if it said that the population of flower beetles triples each week? Then probably this would be a 3 right here. These numbers are not accidental. It's not a coincidence. That is exactly why you see a 2 there. And that is exactly why you see a 30 right there. Too many bugs. There's probably other bugs too. Where there's flower beetles, there's probably other things that you can't even see and count. Okay, the second problem. An initial population of 20 rabbits triples every half year. The function f of x equals 20 times 3 to the x gives the population after x half-year periods. How many rabbits will there be after 3 years? So what does this mean, every half year? No, every 6 months, right? Just think of it, don't make it super complicated. It would be like every 182 days or something like that. But just go with 6 months. 6 months is a half a year. So notice that we have this 20 rabbits, triples. Where do we see that in our equation? There's the 20 and there's the 3. Yeah, just like we talked about. So it makes sense that those numbers are in the equation. Now, it gives the population after x half-year periods. Then we want to know how many rabbits will there be after 3 years. So what do we need to do here? Convert 3 years to half years. If we're talking about 3 years, then how many half years have we talked about? 6 half years. So I'm going to turn this 3 years into 6 half years right away so that I don't forget. Because otherwise I'm not going to have nearly as many rabbits as I should in my answer. Okay, now what are we going to do? Yeah, it's ready to be substituted now. So I'm going to write f of 6. That's just saying I'm plugging 6 in for x equals 20 times 3 to the 6. 14,580 rabbits. And we started with 20. That's an insane amount of rabbits. It's a good thing we have hawks and fox and wolves and dogs.
Maybe they got the rabbits.
Cats. Maybe. Snakes eat rabbits too? Yeah. Not to mention highways, they probably chew up a few here and there. But lots of rabbits. And this is actually pretty true. The population, a rabbit population left undisturbed will show this behavior. Every half year the population triples. Back to graphing. We want to graph y equals 3 times 2 to the x power. We know that it's going to look like a sort of a hockey stick, but we don't know exactly how it's going to look unless you remember back at that table that we were looking at. Because that's a positive number, and because this number right here is bigger than 1, this thing's actually going to wind up looking like that. That table's really helpful for figuring out what the function's going to look like when you graph it. So, we still need to make a table and plot points. We don't have any other way of graphing these. So we need to make an x and a y, and I'm going to pick lots of points here. Pick some easy numbers. Yeah, the usual easy numbers like -3, -2, -1, 0, 1, 2, 3. And then maybe from there we'll have to pick more numbers. So let's take care of the easy ones first. Probably 3 is easy. I'm going to work backwards on this table. If I plug 3 in right here, then I have what? 3 times 2 to the 3rd power. What do I have to do first? Exponents come before multiplication. So I have 2 to the 3rd power first, which is 8. And then times 3, which is, all right, 24. Am I going to be able to graph that? No, that's way off my graph. That's okay. Maybe I'll change the scale later. Okay, take 2 and plug it in. Yeah, so 2 squared is 4, and then times 3 is 12. Am I going to be able to graph that one? Not unless I change my scale. Okay, plug in 1. What do we get? 6. Because 2 to the first power is 2, and then times 3 is 6. Plug in 0, what do we get? 2 to the 0 is 1, but then 1 times 3 is 3. All right, now we got to remember how to work with negative exponents. So we plug in negative 1, and what happens? Yeah, 2 to the negative 1 is 1/2, and then times 3 becomes 3/2. What about to the negative second power now? Plug in the negative 2. 1/4 times 3, which is 3/4. Plug in negative 3 now. Yeah, it's 3/8. Do you see what's happening each time? Like if I plugged in negative 4, what would it be? 3/16. And then 3/32, and then 3/64. Okay? So see that pattern. Each time we're dividing by 2, going backwards. Each time we're multiplying by 2, going forwards. All right, so we can probably graph all of these numbers up to here. So I'm not going to change my scale. We have negative 3, 3/8. So that's negative 3, and then 3/8 is almost halfway. Negative 2, 3/4, 3/4 of the way. Negative 1, 3/2, that's 1 1/2. 0, 3, oops, went up too far. And then 1, 6, all the way there. So we know this is supposed to look like a hockey stick. This is going to go like this here. What's it going to do to the left? Yeah, it's going to flatten out. Is it going to cross the x-axis? No, there's no way. Even if I plug negative numbers in up here, there's no way for me to get a negative result. I'll never be on this side of the x-axis. So it will get closer and closer and closer. Oops, closer and closer to the x-axis. Maybe I should do this without my right hand. There we go. But it will never touch. It will never cross the x-axis. So there's your graph. And that's how you do these. Make a table of values. Usually negative 3 to positive 3 will work. If numbers get too big to fit on your graph, either change your scale or just call it good. That's what we did right here. We called it good. Okay, we have one more. Y equals negative 1/2 times 3 to the x power. So just out of curiosity, what will this one look like? In general, like what's the graph going to look like? It'll look like a hockey stick, for sure. Okay? But now the question is, will it look like the graph we just had? Will it look like that? No. Why not? Because of the negative sign right here. So will it look like this then? No. Why not? Because this number right here is going to make the graph grow, not shrink from left to right. It's going to go farther and farther away from the x-axis. So it'll look more like this one compared to this one. But with that negative sign, instead of looking like this, it's going to look like this. This is the one that we should wind up with. So it's helpful to have that in mind before you dive into the problem, because if you start making mistakes and you're not seeing what you think you should see, then maybe it's because you're doing something wrong. So again, we need to set up a table, and we're going to pick some easy numbers here. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Okay, maybe that works. Do you want to start with the hard numbers or the easy numbers? Start with the bottom. If I take 3 and I plug it in up here, I get 27. 3 to the third is 27. But then I got to multiply it times negative 1/2. Okay, negative 13.5. We are, after all, graphing, so the decimal there is okay. Negative 27/2 would be the exact answer. Okay, I plug 2 in. What do I get? Well, 3 squared would be 9 times negative 1/2. What do we get? Negative 4.5. Negative 9/2 would be the exact answer there. But again, we're graphing, so we can handle negative 4.5 a little bit easier. Okay, I plug 1 in. What do I get? Negative 3/2 or negative 1.5 is correct. I plug in 0. What do I get? Negative 1/2, negative 0.5, same thing. All right, I plug in negative 1, and what do I get? Just think about it. I plug negative 1 in right here. That becomes 3 to the negative first power, which means 1 over 3 to the first power, which is just 1/3. So I have negative 1/2 times 1/3, which gives me what? Negative 1/6. Take negative 2 and plug it in. 3 to the negative second power, which is 1 over 3 to the second power, which is 1 over 1/9 times negative 1/2, which is negative 1/18. Is that a pretty big number? It's a really small number. And then we'll do negative 3 as well, just to see how ridiculous it is. We have 3 to the negative third power, which would make 1 over 3 to the third. So that's 1 over 3 to the third is 27. So 1/27 is what we're looking at. But then times negative 1/2 would be negative 1 over, 54. Really small number, but it's negative. So we got to make sure we graph that correctly. All right, most of these are going to fit on our graph, so let's go ahead and graph them. We have negative 3, which is here, and then negative 1/54. What am I going to do? I'm going to move my marker down 1 pixel. Oh, I can't even do it. 1 pixel right there. There's my dot. It's so small I can't even do it on this board. Then negative 2, negative 1/18. So maybe just a little bit farther down than the last one. Negative 1, negative 1/6. Barely lower than the last one. Then 0, negative 1/2. I can do that. That's easy. And then 1, negative 1.5. Also easy. 2, negative 4.5, 1, 2, 3, 4.5 is right there. And then 3, negative 13.5. So there's negative 7. 8, 9, 10, 11, 12, 13. Be down here somewhere. I got space to do it, so I'll go ahead and put that dot on there. And the nice thing about putting that dot on there is it gives me something to shoot for as I draw in this curve. If I don't do that, then maybe I wind up over here, which would then be wrong. So that extra dot off the grid is helpful. So very carefully draw in your graph. Make sure you don't cross that x-axis like I just did. Maybe I should use my right hand. Curve around, and there you go. See, I totally missed my dots, but that's the idea. I don't know. Maybe I should drink some coffee or something. It's terrible. I don't even drink coffee. So that's how you do these graphs. Set up a table. Take care of the exponent first, then multiply times that. Most of the stuff you can do in your head, but if you can't, use the calculator. That's fine. Okay, I just want to check that graph on the calculator here. So on your calculators, you can get to the graph quickly if you're just doing a graph by pressing the calculator button. That takes you to the calculator, but if you press it one more time, it takes you to the graph. So here we are. And I just want to type in that function right there, just exactly the way that I see it. So I start with a negative sign, which is that button. And then 1/2, so type in 1 divided by 2. And then times 3. And then your exponent button is this little caret guy right here. So 3 to the, and then we type in the letter x. And notice that it gives me the negative 1/2 times 3 to the x. I can see it all written out right there. So then I press enter, and there's my graph, just like what I came up with. It even graphed it in blue, just like I did, which is awesome. What? Red? That's terrible. It's okay if it's in a different color. The default first color that these calculators use is blue, and then the next one is red, and then like green, and then it goes to raspberry and some other sorbet type color. Pink, orange, you know. So the color doesn't matter, but the point is the graph that the calculator gave me is the same as the graph that we came up with. And if you look, does our graph cross the x-axis? No. Does it touch the x-axis? It looks like it does, but if we were to zoom in on this, we would see that there's actually a little gap between our graph and the x-axis. So that's kind of the limit of the way that we graph things. We can show it when we graph it by hand. The calculator is going to make it look like it kind of is riding that x-axis, but it's actually not. It's just getting closer and closer without actually touching it. So that's all I needed to do to show you this. You can graph these on your calculator to check what they're supposed to look like. But if you're supposed to do this by hand, if I give you a grid, then I need to see the table, and I need to see your work, and then I need to see points plotted. I can't see just a sketch. That way I'll know that you just graphed it on a calculator and then tried to match it on your grid. That doesn't work. You have to actually do this by hand. Okay, that's the section.